Electromagnetic induction. The first productive experiment concerning the effect of time-varying magnetic field were performed by Michael Faraday in relation between the change in magnetic field and the current. So the electromotive force EMF is induced when magnetic field in the coil is changed by pushing the bar magnet. This is a bar magnet, so we push the bar magnet in and out. For example, in the first picture, as you can see here, so this is a bar magnet and this is a coil. So the bar magnet is moving towards the coil, so the coil produces a current. So in order this current have a magnetic field, as you can see here, the current is going upward. So when you see you apply right hand rule, so the magnetic field produce north pole. This coil produce north pole in the left side, south pole in the right side. As you can see here, the north pole is approaching this. The north pole of the bar magnet is approaching the coil. So the coil must produce a north pole in order to oppose this one. So when this one approaches towards the coil produces a north pole for just opposing the motion of this bar magnet. Okay, so in this one, in the second diagram, you can see that this bar magnet, again the left side is north pole, the right left side is south pole, the right side of the magnet is north pole, but it's moving towards the left, the bar magnet. So this coil also produces such type of pole in order to oppose the motion of this one. So this one is moving towards the left, so this coil should produce in the left side south pole, in the right side north pole. So the south pole attracts or opposes the motion of this bar magnet. For this, the current will go downward. Applying right hand, the current direction is downward, but for this one the current direction is upward. Anyway, so there is an induced electromotive force due to the motion of this bar magnet. So there is also another thing. Instead of moving this bar magnet, it's also possible to move this coil in and out, or towards this magnet or away from the magnet. With that, we also produce a current. Sometimes if the motion of this bar magnet and this one is constant or similar, so in such cases you'll get the same current. Okay, now let's proceed to the next one. Movement of a magnet relative to the coil produces EMF. Movement of magnet. When the magnet goes towards the coil or away from the coil, so it produces an EMF. The same EMF here, you can see that the same EMF are produced if the coil is moving relative to the magnet. So instead of moving the coil, as you can see here, let's go back and see. Instead of moving this bar magnet, it's possible to move this coil in and out. And with that, if the motion of this one is similar to the motion of this coil, then the produced current in both cases will be the same. So you make this one fixed, the bar magnet fixed, and it's possible to move this coil in and out. Okay, so here we can see that the same EMF are produced if the coil is moved relative to the magnet. Electromagnetic induction occurs when an EMF is induced in a coil due to changing magnetic flux. So the main thing that we can see here is the change in magnetic flux. So the change in magnetic flux occur in a coil. So due to that, there will be a production of current. So the law of electromagnetic induction says that Faraday law states that the size of induced EMF, amount of our induced EMF is proportional to the rate of change of magnetic flux. This is the rate of change of magnetic flux. Phi indicates magnetic flux, and this indicates the rate of change of magnetic flux. So the induced EMF is proportional to the rate of change of magnetic flux. If the rate of change of magnetic flux is larger, therefore the induced EMF is larger. So the other one is Lenz's law, states that the direction of the induced EMF is always such as to oppose the change producing. So that's why here we have a minus sign. This is a minus sign. So the induced EMF is always to oppose, says the direction produced EMF is always as to oppose the change produced. Yes, as we have seen there, when the bar magnet is moving towards the left or away from the coil, so the coil will produce a magnetic field in order to attract the bar magnet which is moving away from it. So in conclusion, now we are in a position to calculate the induced EMF. So induced EMF is equal to this is number of turns of the wire, so multiplied by this one is change in magnetic flux, or the rate of change of magnetic flux. Remember Faraday's law, the size of induced EMF is proportional to the rate of change of flux. In this case, the proportionality constant turns out to be n. This one is proportional to the rate of change of magnetic flux. Therefore, the proportionality constant is taken to be n number of turns. Okay, now let's proceed to the next one. This is the best example that we have. It says that the square coil of, as can be seen in the figure below, has side length which is equal to 0.2 meter long and is tightly wound with number of turns is 200 turns of wire. The resistance of the coil is, the coil resistance is 5 ohm. The coil is placed in special uniform magnetic field that is directed perpendicular to the face of the coil and whose magnitude is decreasing at a rate of change in B. Change in B over change in T is equal to, remember it is change in B over change in T is equal to minus 0.04 Tesla per second. So the first question is, what is the magnitude of EMF induced? Now let's solve this one. EMF induced is equal to minus, let's go back to the formula. Induced EMF is equal to minus number of turns, change in flux, or the rate of change of magnetic flux. So we know that flux is equal to, so the magnetic field P multiplied by B multiplied, this one is B multiplied by area. So it's possible to replace this one B, change in B with area. So the induced EMF, when we modify this, when you modify the formula, the induced EMF is equal to minus n, which is number of turns, multiplied by the area, multiplied by change in B over change in T. So now let's go back to the question, and this is one of the question. Change in B over change in T is already given. So the area, which is square of the side 0.2 meter. So if you want to find the area of a given square, the area is equal to 0.2 multiplied by 0.2, which is equal to 0.04 will be the area. And number of turns is already given, which is 200. Area is given, number of turns is given, and this one is already given. So the final result will be, you know that phi is equal to B times area. So the area is length squared. So the EMF is equal to number of turns, change in flux over change in T, and phi, which is equal to B times the area. So it's possible to write n multiplied by the area. Change in B of change in T is equal to 0.04, and the area is 0.2 meter square, which is 0.04 multiplied by 200. Finally, the induced EMF due to this 200 turns of coil, square coil of length 0.2 meter, so which faces this magnetic field, will be equal to 0.5 volt. That is the first result. Okay, so the second one is, what is the magnitude of the current circulating through the coil? So in order to find the current, we have already EMF value. There is also resistance, so it's possible to apply Ohm's law, where the EMF is equal to I times R. I is equal to the EMF value divided by resistance, which is 0.5 divided by this resistance is already 5 ohm, and EMF is 0.5, so 0.5 divided by 5 ohm, which is approximately 0.1 ampere will be the answer. Okay, now let's go back to the other one, which is about insulator, conductors, and semiconductor. Before we look each one of them, now let's see this one, insulator conductors found in electronics. So electronics is one of the branch of physics and technology concerned with the design of circuit using transistor, microchips, capacitor, resistor, inductor, and so on, and with the behavior and movement of electrons in a semiconductor, conductor, and the vacuum tube or gas. Okay, so all modern gadgets, like as you can see, this television, these computers, this automatic washing machine, and these CD players all use microprocessor recently. So having integrated chips, which consists of large number of logic gates. In each one of them you'll get microprocessor. This microprocessor includes large number of logic gates, and this logic gates contains transistors, diodes, resistor, and capacitors, which are built in, so it's impossible to see by our naked eye. But you may get thousands of transistor within those micro processors. So all this use this the IC, integrated circuits, that contains a different number of logic gates. So this logic gates actually contains OR gate, NOR gate, NAND gate, NOR gate, NOT gates, and so on. So the diodes actually contain a P-type, N-type semiconductor. So transistor is built from N-type, P-type semiconductor, which contains emitter, base, and collector. Resistor, there are different types of resistor. The most known types of resistor is the carbon resistor. Okay, now let's go to the materials. Materials are classified as conductors, insulator, and semiconductor according to their electric conductivity. Insulators, conductor, and semiconductor. As you can see, the band gap is larger for insulator, and for semiconductor it's small, but for conductor the band gap overlap. This is no band gap here. As you can see here, the conduction band and the valency band, they overlap with each other. But here, this is the line of Fermi level. This is the line of Fermi level. As you can see here in the insulator, this is very large band gap. So the electrons, they are unable to move, or they need a very large energy in order to move from this valency band to conduction band. But for semiconductor, they need smaller than this one in order to move the electrons, in order to move from the valency band to the conduction band. But in conductors, they are easily moving from the valency band to conduction band. So these conductors, they are easy for conduction of electrons and for electricity, but this one actually used for insulating purpose. Okay, but the semiconductor is different from this insulator and conductors by using doping process. It's supposed to have conduction better than the pure semiconductor or intrinsic semiconductor. Okay, there is also a change in its behavior during the high temperature. There is a change in conduction. Okay, Now let's proceed to the next one. So the energy band gap diagram. This is the energy band gap diagram for good conductor insulating semiconductor shown below. This is a sample, as you can see here. For insulator, there is a valency band and there is a conduction band. So it says empty. No, we can empty conduction band. So the electron needs to get here in order to remove this this empty conduction band. So, but the energy that's needed is greater than 3 electrovolts. But for semiconductor, it is less than 3 electrovolts, which is much better than the insulator. But for conductor, nothing because this is the conduction band and this one is the valency band. So they overlap each other just like this. We don't need this much amount of electrovolts. Okay, the other important thing that we need to see is the characteristics of conductors. The substances which conduct electricity through them in greater extent are called conductors. In conductors, the conduction band and the valency band overlap, as we have seen in the previous slide. So in conductors, the conduction band and valency band, they overlap. One overlap with the other, with each other, or gap between them is very small. There are free electrons in conduction band. Free electrons in conduction band for conductors. Due to increasing temperature, conductance decreases. There is no effect of addition of impurities on conductivity of the conductor, just like that of semiconducting material. So the conductivity range varies from 10 raised to 4 to 10 raised to 7 ohm meter. That is the conductivity range. Characteristics of insulator. Insulator, the conduction band and valency band are widely separated. They are far apart. The conduction band and the valency band, they are far apart. So the electrons need sufficient, very large sufficient energy in order to move from the valency band to the conduction band. There are no free electrons in the conduction band. Just like that of conductors, we don't have free electrons in the conduction band. In that of insulators, there is energy gap between conduction band and valency band, which is more than this much amount of 3 electrovolts energy gap is there. So you need this greater than this 3 electrovolt in order to move electrons from valency to conduction band. In insulator like diamond, the forbidden energy gap is quite large, having a value which is 6 electrovolt larger than 3 electrovolt. So the minimum of 6 electrovolt energy is required for electron to move from the valency band to the conduction band. There is no effect of change of temperature on the conductivity of insulator. But there is effects for semiconductor. There is no effect of addition of impurity like that of semiconductor again on conductivity of insulator. They have very low conductivity ranging between 10 raised to minus 10 and 20 and 10 raised to minus 10 per meter. Okay, now let's go to the next slide, which is about characteristics of the semiconductor. So in semiconductor, the conduction band and valency band are very close to each other, which is much better than that of insulator. Or the forbidden energy gap between them is very small. The forbidden energy gap is approximately 1.1 electrovolt for silicon, which means you need this much amount of energy in order to move electrons from the valency band to the conduction band. The electrons of valency band can easily be excited to the conduction band. But for insulator we need greater than 3 electron volt. That's why here we need a very small energy. So there is energy gap between conduction band and valency band, which is less than 3 electron volt. Due to increasing temperature, conductance increases. Conductance increases or proportional to the temperature. So there is an effect of addition of impurities. So addition of impurities, which is called doping. So whenever we say impurities like phosphorus, boron, arsenic, and so on are considered to be impurities, so they can be added on this pure silicon or germanium, so in order to get holes and free electrons, so that will change the conductivity of the material. Their conductivity range from 10 raised to minus 6 and 10 raised to 4 per meter. Okay, so now let's look this semiconductor, the different types of semiconductor. The first one that we have is intrinsic semiconductor. The second one that we have is extrinsic semiconductor. So the intrinsic semiconductor is called the pure form of semiconductor formed by covalent bond. As you can see here, we have silicon. The silicon, which is the atomic number is 14, so 2 in the first shell and 8 in the second shell. In the outermost shell of the silicon will get 4 electrons. So this one also have 4 electrons in the outermost shell, so they are covalently bonded with this neighbor. So this one, this is with the other one, with this one, so this one bonded with this one, so we have 2 electrons here, 2 electrons, 4, 6, 7, and 8. So this is a covalent bond, so they are formed by a covalent bond. So it is pure form of semiconductor. Pure form is called intrinsic semiconductor. You can have also germanium. So when you come to the extrinsic semiconductor, it's not a pure form. So in this case, there is also addition of impurities. Due to the addition of impurities, or due to the different types of impurities which is added on the pure semiconductor, which is added on the intrinsic material, we have again 2 types. The first one is P-type, the second one is N-type. So when do we say P-types? When boron or trivalent element like boron added on the pure intrinsic semiconductor, we will get extrinsic semiconductor, and from the extrinsic type it is under the category of P-type. When you add boron on the pure semiconductor, you get a P-type semiconductor. But when you add phosphorus, which is atomic number 152 in the first shell, 8 in the second shell, and 5 in the outermost shell, 4 of them covalently bonded with silicon, and 1 electron will be left. That's why we say it is N-type. But for this one, when you add boron, which is 2 in the first, 5 atomic number is 5, 2 in the first, 3 in the second, so which is 1 electron is left. That's why you say P-type. So the majority carriers in a P-type materials are holes. The minority carriers in a P-type materials are electrons, whereas the majority carriers in N-type materials are electrons. The minority carriers in N-type materials are holes, because we have large number of electrons as compared to the minority carriers, which is holes. So this is the energy gap. We have a valency band and conduction band, and the Fermi level is present in here. Okay, now let's proceed. So N-type semiconductor. In order to get N-type semiconductor, a pentavalent element will be added on the pure intrinsic semiconductor. So the pentavalent element, one is phosphorus, or we have this also pentavalent element, antimony or arsenic, is added to pure silicon crystal intrinsic semiconductor. So in order to get n-type semiconductor, pentavalent elements are called donor impurities. These pentavalent are donor impurities. They deliver free electrons, but trivalent elements are acceptor impurities, as they donate this one pentavalent element or donor impurities, as they donate electrons without creating holes. They donate electrons without creating the holes. So the majority charge carrier of electrons are the order of 10 raised to 24, whereas the minority charge carriers holes are 10 raised to 8. As I told you before, the majority, as I told you before, the majority carriers in any n-type semiconductors are electrons. The minorities carriers charge carriers are holes. So the majority carriers, which is about 10 raised to 24, but the minority is 10 raised to 8. This is a very large number as compared to this one. That's why it says the majority charge carriers. Okay, so as you can see here, this is an example of n-type semiconductor. This is silicon, but in the middle we have arsenic. So arsenic has 5 electrons in the outermost shell, then the 4 of them bonded with the silicon, one on the left side, right side, up and down, so 1 electron will be left. This left electron comes from the arsenic. This is a left electron because it contains 5 electrons. So the 4 will be bonded with silicon, but 1 will be left. That's why we get the majority carriers. They are electrons. Majority carriers in n-type are electrons. The minority carriers in n-type are holes. But for p-type, the majority carriers are holes. The minority carriers are electrons. Now let's proceed to the p-type. When trivalent element like indium, aluminum, boron is doped with pure silicon, the added impurity atoms replace some of the silicon atoms here, and when trivalent elements, so told you before, like boron, aluminum, indium is doped with pure silicon, so we get a majority carriers. They are holes and minority carriers are electron. This is an example that we have here. This is a boron, so the 3 of boron electrons, that is 1, 2, 3, will be covalently bonded with silicon, but there is 1 left. So this is acceptor impurity creates hole. It creates, this is a B acceptor impurity, but these are donor, so it creates hole. But there is this one donor impurity, they contribute electrons, phosphorus, so the antimony will be considered as n-type material. Okay, now let's proceed to the next slide, which is about diodes. So now we have seen n-type and p-type. So having the n-type and p-type, now we are going to build this one, diodes. So the semiconductor diode is a fundamental two-terminal electronic device. Similar to a resistor. A resistor has 2 terminals. Okay, so the volt ampere via a relationship of a resistor is simple, which is linear relationship. So when you increase voltage, there is also a proportional increase in the current. That's why we get linear. But the VI or the VI characteristics of diode is not linear. Characteristics is not only linear. It's not linear. It is only non-linear, but also depend on the operating condition. So there is also VI characteristics drawn for forward biasing and reverse biasing. We will see what forward biasing and reverse biasing. So the diode actually contain p-type and n-type material. So if the p-type is connected to the positive terminal and n-type is connected to the negative terminal, in this case it is forward biasing. But if p-type is connected to the negative terminal and n-type is connected to the positive terminal, so it's reverse biasing. So when you come to here, a diode allows current to pass through it in one direction. So it acts as a switch in electronic circuit. Why it acts as a switch? It passes current in one direction, it will reject the current in a reverse direction up to a certain limit. So at the room temperature, a piece of P-type material has a majority holes, antimatter has majority charge carriers are electrons. When a part of intrinsic semiconductor piece is doped with a pentavalent impurities, the remaining part is doped with trivalent impurities. So that is a fabrication method of doubts. We will take intrinsic semiconductor, one intrinsic semiconductor just like this, certain gap. So on the one side we dope pentavalent element, on the other side we dope trivalent element on one intrinsic semiconductor. With that, it is possible to build